Ah, perfect. Okay. It wasn't speaking. I just wasn't my Zoom. I don't know if any of you run into this with Zoom all the time, but it literally demanded that I relog, even though I'd already opened this page, I had to relog. And true confessions, apparently I don't know about crosswalks and traffic signals. I thought I was good at recognizing those sorts of things, but I mean, I think I might actually be a robot because I always fail those. But I've decided from now on, whenever I go walking my wife and kids, whenever I get to a real intersection, I know how to test whether they're a robot or not. If they don't recognize the crosswalk or the traffic signals, then I know they're not really my family members. But anyway, I'm so utterly sorry that just the sad part, the technology issue that I was having, really just came down to the fact that I could not recognize traffic signals. Okay, so here are the things that are up today. So a bunch of electrochemistry popped in. So for some reason this isn't driving. So hopefully you can see various questions. So mostly from phase one. A couple people submitted something from today's lecture, so I want to go over that. And then some physics from book one. And so hopefully that'll cover most everything. And apologize, but yeah, the terpenes, and then just a couple sugar questions were in there. But hopefully if we're geared up and ready to go, I think, let's see, yeah, everybody submitted is here, so we're good to go. And I'm not good to go. For whatever reason, I don't know why this is doing it. I'm so sorry. I need to figure out what all I have open because it keeps on connecting to a totally different lecture. And I can't blame the electronics anymore. I have to take personal responsibility on this one because I haven't properly named my devices. So I basically, here we go. I was opening up my other computer. Okay, after all that, here's our MCAT. And honest answer, is it cute or annoying at this point that I start off every office hour making you look at the MCAT? Okay, it's still cute. Okay, when it hits that annoying point, let me know. But I still think it's kind of random. Okay, so starting into GChem, electrochemistry specifically, just a heads up, electrochemistry is a highly tested topic. So one of those you definitely want to make sure you have the logistics down pat, how circuits work, or well, I should say electrochemical cells work, how a voltage source in a circuit works, just how it connects to everything. Little cuteness never doesn't hurt anybody for the most part. Okay, so what problems occur when you apply voltage greater than 1.6 to an aqueous metal halide over a long duration of time? Okay, so I want to make this a bigger question than just what's going on here. But if you have multiple reactions that can occur, in general, what occurs? The hardest, the middlest, or easiest reaction, generally speaking? Easiest, just how it works. But every now and then, can you get complications of side products, other things happening, if they're possible? Okay, so that's what we're dealing with here. So in aqueous metal halide, so I'm just going to randomly pick metal 2 plus 2 electrons going to a metal solid, and then H plus 1 electron going to 1/2 H2 gas. Those are competing reductions that can happen. And the competing oxidations that can occur would be the halide going to 1/2 X2 gas plus an electron, and then OH minus going to 1/2 O2 gas plus H2O plus an electron. Okay, and for that one, it's a little bit tricky because I haven't balanced correctly. So if you can deal with what I've done. So if you can just deal with that part and forgive me for not balancing it all the way. Not yet. So I've got a question. Can I draw an electrochemical cell? I don't want to deal with that yet. I will get to it, but for now, I just want to care about what I'm dealing with in terms of what competes. So if I have a solution, I'm trying to reduce it down, and I have two things can be reduced and two things can be oxidized, then I have to decide what's going to occur. Okay, so within the cell, is this an electrolytic or galvanic cell we're talking about? I'm looking for one other thing. And so the general rule is this. A galvanic cell is naturally occurring or you have to power it. Naturally occurring. But if you have to add power into it, is it galvanic or is it electrolytic? So is there anything in this question that gives me a hint that it's electrolytic? Okay, so we're applying a voltage. It's like, okay. So that means the following is going to be true. I'm going to draw my anode and cathode as such just because I like to do it this way, but that's my cathode. That's my anode. This is my anode, this is my cathode. And it honestly doesn't matter which way I draw it. I'm just going to set this up. But if I do 1.86 volts, then I need to start looking at what these can be. And so in specific, this is 0 volts, and this is negative 1.86 volts. So is it possible that H2 gas and OH minus can react to form O2 gas? So would 1.86 volts applied be enough to force the water reaction to occur? Okay, so let's get rid of the things that are ridiculous. Will the halides become cations? Well, they lose so many electrons. So becoming neutral is one thing, but would halogen ever want to become Cl plus, Br plus, F plus? That's definitely not going to happen. And do metals ever want to become anions? Sodium minus, potassium minus. Those two are just not going to happen. I think that's, you just have to have enough experience with chemistry to say metals are either neutral or cations. They do not become negative. Halogens are either neutral or negative. Halides, they don't become positive. So are we worrying about adding voltage and forcing hydrogen go to H plus, or H plus going to hydrogen? Are we worried about O2 going to OH minus or OH minus going to O2? We could potentially get that side reaction. So instead of getting the metal and the halogen that we want, we could potentially end up getting H2 gas and O2 gas. So how many are okay with this? How many are like, I can kind of see that? Okay, so do you believe that you can have side reactions? So if I have in solution, let's just consider everything we have in solution. So we have the solution here, 2 cells, 1 cell with a salt bridge, irrelevant, but in solution, I have my normal metal. I want that to go there. And I have my normal halogen. So I'll say X. And what I'm trying to get to occur is I'm trying to get this metal to turn into cation, to turn into a metal, trying to get the halogen solution to turn into X2 gas and bubble off. Okay. But can I just put salt in there? Can I pour solid salt into this, or does it have to be a solution that things can move through? So do salt particles just randomly move off, or do they have to be in a solvent? Perfect. So solution couldn't interact. So the solution we're adding is water. So these are in aqueous solutions, which means I don't just have M2 plus, there's also H plus because water dissociates ever so slightly in H plus. And it's not just X or X minus, I can also get a little bit OH minus because again, water dissociates into H plus and OH minus, hydroxide and hydronium. And so what we're saying is, if I put a small amount of voltage, let's say 1 volt, that's not going to affect water and H plus because it's not enough to push 1.86. But the 1.86 should just be ding, 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 some little light or some bell goes off, some light that lights up that says 1.86. I've heard that number, I've heard that number. Oh yeah, water is 1.86. So the formation of water, what requires 1.86, the breakdown of water will release 1.86. Yeah, isn't that a weird phrase? But yeah, so the question was, can you hydrolyze water? Yeah, and because we always think of hydrolyzing something else by adding water across it. But yeah, this is actually what's happening here is we're hydrolyzing water in that way. So not an acid-base sense, but in a reductive sense. We're turning in the free radicals, and then we're adding an electron, and it's doing whatever it does. But yeah, hydrolysis of water is breaking of the water. And would you agree, when you think of hydrolysis, hydrolyze, you agree, you typically think of it in OChem and biochem of using water to break something else. So hydrolysis of an ester, hydrolysis of a peptide linkage, hydrolysis of a phosphodiester. You never think of hydrolysis of water, but that's in this specific case, that's actually what we're doing. Electrolysis is causing that hydrolysis, the breakdown of water. So technically, you should call it electrolysis of water like it is here. But hydrolysis of water to use these two, or hydrolysis to use this. So you're saying we could have gotten rid of it because that word doesn't fit. You know, actually, I like your answer on that sense.
Yes,
yeah,
that's what I was wondering.
Yeah, so that's actually really good language logic. So it's like taking your car skills and applying them in science. Always a good thing if you can figure that one out. But yeah, but technically, yeah, you can undergo electrolysis of water, or you can hydrolyze water if you break that bond. And so it's a phrase we never use, but it's technically not incorrect to say this. That's just not redox. So when we say voltage, redox and not acid base, that would also. Oh, you're welcome. And hopefully this all seems okay. And Tiffany, does it make sense you have competing reactions? That because you have your metal, but also you have water in there, and because you have X minus, but also you have water in there, you have the chance of either the metal or the H plus, and then anion. And so in general, again, answer this for me. What reaction would it want to do? The hardest, middlest, or easiest? Wants to do the easiest, whatever it can. So it wants to do the lowest possible voltage reaction. So I apply 1.86, which can do any combination, but it might prefer to do this. You might only get a little bit H2 and O2, but if these become close in value and these become close in value, you're going to get more and more H2 and O2 forming. Yep. So in other words, let's say I have a salt bridge, or let's say I have a membrane, or whatever I've decided to connect it to with. Can ions continually go in, transfer over to the other side, which means they can be either in solution in the membrane or bridge in the other solution. So yeah, entropy is going to kick in. Things are free to go across that bridge either way. So is that true? Can a bridge only allow one directional flow, or does it typically allow both traffic? You can go left to right, you can also go right to left. So they can be in solution on either side, they can move across. In an ideal world, we don't want the cations to bleed over, but reality is, do batteries eventually die out? Yeah, and they do sometimes when you just get entropy kicking in. Okay, so hopefully this seems okay. Yeah, I want to address that. So here's the question. So cations and anions are not stuck in the salt bridge, but submerged in solution in electrodes. They're kind of both. So basically, there's always a gradient. there's always something going on where if I have ions here and a bridge is moving across. So it's kind of like if you have two sides of the city, east and west, and people, let's say, live in the east mostly and work in the west, or vice versa, then can you say people are always on the bridge, never on the bridge, or sometimes people on the bridge, sometimes people here, sometimes people there? It's always a moving dynamic because they're free to go either way. So I can't really answer your question per se other than this. Ions can go in, they can move across, but at some point it's going to be ions in there, but not necessarily the same ion. It might go across and come back, go across and come back, but there's always somebody crossing the bridge. There's always ions here and ions here. So hopefully that seems okay. All right. I believe this is the same passage. Let me see, same page number. Yep. Okay, so metal purification using which of the following salts require the least applied voltage? How do I figure this one out? What am I actually looking for? And how many give me permission to be really lazy? So I want to be lazy as can be. I want to just look at my table here. So for Ag, I'm sorry, I hit the wrong halogen. So for choice A, Ag and Cl is going to be 0.8 plus 1.36. And have I done it the correct direction or no? Okay, which one needs to be reversed? So which one is correct in metal purification? So metal purification meaning I'm making a metal salt or a metal solid. So I'm starting with the salt, but to get a pure metal, so metal purification is the generation of a pure metal. So that is what I'm going for here, and I need to reverse this. So what we're saying is, in essence, I'm going from Ag plus and Cl minus, going to Ag solid plus 1/2 CO2 gas. That means this number here, 1.36, needs to be a negative. Because I'm actually doing the chlorine in reverse. So in order to get a reaction, it has to be redox. Everything here is red or ox, even though it says it right there, and it's kind of a silly question, sorry. Everything's red. So I need to reverse the reactions at least every single time. I have to reverse at least one half reaction. Okay, so let's do copper. I'm going to do different colors. So copper bromide. So bromine's here, copper is here. So copper is 0.34 plus now a negative 1.09, excuse me. Equal negative 0.075, I believe. And please double check my math because I forget. I can't remember if I tell you the truth or I lie. And actually, am I telling you the truth that I can't remember? Okay, I'll move on. Nickel bromide. So in this case, a negative 0.23. And actually, you know, my screen is blocking it, but it is a negative, right? I have it pure memorized, but I can't actually read the nickel number. But if I remember right, it's negative 0.23. Hopefully it matches. Okay, oh, no problem. I will click away. You return. Casual flex. I have no idea what that is. Oh, the fact that I've been doing this long enough that sort of yeah, I'm now finally realizing it. Yeah, like, hello, I'm just picking up this pencil while I flex. Okay, I get it. I think it's more along the lines of, I've been doing this for so freaking long that, I mean, just long story short, but yeah, I just have so much of this crap program in my head. Although on the bragging thing, I memorized state capitals in 4th grade, and for some whatever reason, I still have those. I still have all my stupid state capitals memorized. So that's a not so casual flex on that one. And that's been really helpful in life. I mean, I found that really has done me a lot of good having that memorized. Okay. Oh, capital of Utah? I mean, assuming it's, oh my gosh, Salt Lake City, I was going to say, but it might be Provo. So, yeah, I knew I'd be called on it. Yeah. Okay. So, as far as this goes, does it make sense why this number is getting reversed? Why I'm not taking the positive, why I'm taking the negative of it? Okay, so perfect. So yeah, it's negative because it's got to be reversed in the reaction. So I'm leaving the metal as is. Can I go into a metal because I want to isolate the metal? So that one stays as is, straight from the table, but I reverse the halogen and add it together. So which one is going to be easiest to reduce? Negative 0.56, negative 0.74, negative 1.32, or negative 2.12. So it's asking for the least voltage. Okay, so I like what's going on here. The numbers that were submitted were either A or D. Why would I like that? Just from a test taking standpoint, why am I happy absolutely nobody put B or C? And at the very least, please recognize that as just why would B and C be the worst answers if you were thinking along those lines? Not necessarily close, although that sometimes is the thing here. They're not an extreme. This is asking for an extreme, either the most or least of what I need to do means I need either the least or the most of what's going on. You agree? If we need the least, then there's something smaller than this one in magnitude. I need the most, there's something bigger than that one in magnitude. So because it's an extreme question asking for least or most, greatest, smallest, some extreme, you need an extreme. So test skills would say get rid of B and C right away. So you're down to 2 choices. If this is how much voltage the reaction would give off, which is actually absorbing, does that mean to make this one go, I need to add 0.56 volts or more. That was really bad. So I need to add over 0.56 volts. For this one, I need to add over 2.12 volts to make it go. So this is what it would go. So I need to couple it with something more favorable. So best answer? Perfect. But before depression or celebration or any sort of emotion, Brooke, why do you not pick B or C? Perfect. Yeah. And I really want to emphasize that. And so it's nice to get the right answer. It always is. But sometimes there's something you got to give yourself a break when you realize, hey, I zeroed in and went the wrong direction. That's fine. I can correct that. The really big thing is, I think, getting rid of B and C on this one. I think that's the most. And exactly, that stupid sign convention of delta G as opposed to voltage. Because voltage is a physics term, so positive is favorable. Delta G is a chem term, so negative is favorable. And all I can say is you should be angry at chemists and physicists for not being on the same page. So what are the odds that could potentially happen again? Because we do the same thing over and over and over in chem and physics. Yeah. And so hopefully getting burned this time and maybe 1 or 2 more times, by the time the real test comes around, you're going to discover touching hot things bad. Okay. For this one, there's so many different ways they can write cell notation. And my goal is to constantly mess with you. It gives me not only job satisfaction, but it also is a good preparation skill. So what occurs at the anode? Oxidation or reduction? Oxidation. Because what kind of an animal is Leo? You know, our famous friend Leo who says grr. Leo is a red cat. Perfect. So let me just, again, go back to that. Leo, the red cat, says grr. Sorry, I'd like to do that. Leo, red cat, says grr to the oxen. Oxidation of the anode, reduction of the cathode, lose electrons oxidation, gain electrons reduction. So our mnemonic's a bit cumbersome, but does it cover everything? Do I have anode, cathode, oxidation, reduction? Is it actually the power mnemonic with pretty much everything you ever want to know about redox all in one spot? You bet. Okay, so that means these are oxidations, so these need to be taken directly from the table or reversed. Got to reverse it. So this is a positive 0.23. This is a positive 0.76. This is a positive 0.44. And this is a negative 0.80. Whereas over here, it's just reduction exactly as it's drawn. So this is a 0.34. This is a 0.80. This is a 0.34. And this is a negative 0.73. Okay, again, two ways I can look at this. I can do the numbers. I definitely think the numbers are important. So adding 0.23 and 0.34, positive or negative number? Perfect, positive. Adding two positive numbers is still going to be positive. Same thing with choice B. Positive and positive means positive number. Choice C, positive and positive, positive number. And then choice D, positive or negative number. Negative number. One of these things is not like the other. So we have three positives and a negative. What's true of a galvanic cell as far as the voltage goes? The voltage of a galvanic cell is positive EMF. So that one's the one that's off. Okay, hopefully it seems okay. The other way, do you really want to have an overall reaction where you're ruining silver? Yep, positive means it will occur without you having to put work into it. Exactly. So EMFs, again, unlike delta G, positive is good. But then also, do you want to generate precious metal? So if I generate nickel 2 plus, so what? Zinc 2 plus, who cares? Iron 2 plus, rust happens all the time, but silver, that'd be pretty unfavorable. Losing all your silver would be unpleasant. Okay, okay to move on. And actually, before I move on, how many do that sort of thing? Apply whatever common sense rule you can wherever you can. And maybe you don't do it instinctively yet, but when you start doing it more and more and more, yeah, and that's one thing I implore you, beg you, ask you, whatever word I'm fishing for here, to every chance you get, double check with common sense, and you're going to start realizing that you can probably do about a quarter to a third of the questions on the MCAT just based on good old-fashioned intuition and common sense. And so for people who've taken the MCAT before, would you agree every now and then there's a question where the only way you can really get that is just by living life? Every now and then there's a question that you just flat out have to have been alive to watch the world happen to actually get this. So I distinctly remember on my very first MCAT, I thought I have a cultural advantage here because I live in a city with lots of smog. I know that nitrogen-based impurities, nitrogen oxide impurities, cause the brown skies where I live. So I had an advantage just by living. I didn't know it from chemistry. I knew it from going outside, taking a deep breath, and NO2. I mean, those are the kind of things that hopefully make some sense. And so I'll give you this a perfect example of this concept. Yeah. And how many would agree with this? I'm going to quote you if that's okay. I have a tendency to forgetting common sense when I'm taking an exam or in laboratory setting. How many agree with this? How many agree your confidence goes down and you think you're supposed to know it from some scientific brainwashing training, whatever you want to call it, and you can't just use real life? Yeah, I think we all have that. And I honestly believe it's from confidence in that they don't get you don't get reinforcement when your common sense is right. Yeah, you got to build it a little bit. You got to build your confidence, your common sense, and trust them. So let me give you a specific example. So I'm assuming some of you are also from a similar area I am. When you think of smoggy days, are they usually hot or cold days where it seems the smoggiest? Hot days. How many degrees summer? Is it because A, there's more cars driving in the summer, or B, the heat from the sun actually pushes a reaction in the browner direction? So it ends up, here's my reaction. This is a clear gas. That's the brown gas we typically see with smog. There's other components, but that's a common one. Would you describe this then as endothermic or exothermic based on your real life experience of heating it up and having the sky browner? Endo. Because if you add heat, it shifts in the forward direction. It gets from clear to brown on a hotter day, which means heat must be on the reactant side. Treat it like a reactant, goes forward. Heat is entering a reaction. And then common sense or chemistry sense will tell me if I go from one molecule to two, did I probably break a bond or form a bond? So if I'm going from one molecule into two, I'm breaking a bond. Does it take energy to break a bond? Does it take energy to pull two portions of a molecule apart? Sure, sí, bueno. So add your heat in, you break that bond, you turn it from the clear to the brown form. How many realize, like, I know that from just living life? Because how many have seen summer has more disgusting sky, less clear air, more tarnished air, if you will? And reality is, sorry to be the one to break the news to you, air quality, even in the winter, may not be all that great. It's just in a clear form, so I don't see it. But as soon as I breathe it in, temperature goes up. Dang it. So, but for what it's worth, is that something you could get more from common sense and then support it with chemistry than the other way around? And I'm telling you, that logic right there about the brown skies being browner in the summer. So at a heat, it goes to the brown side. So heat must be on the reactant side. That got me points on the MCAT. That got me one question right. So again, really trying to push that. And the question was, how do you build that confidence? I think it's just because you have to celebrate. So how many, when you get something wrong, punish yourself emotionally? How many are guilty of such behavior? Yep, we always do that. When you get things wrong, you, as a pre-med, you count from perfect, 100% on a test, down. If you get a 92, it's like, missed 8. Yeah, phase scores, percentages may not be bueno right now, but you got to see how you're growing. So punish yourself if you get a bad score. That's fine, as long as you always reward yourself when you do something really insightful. I'm telling you, take those 5 to 10 minute little celebrations to say, I got this right. I'm pretty glad I did this. Invest in your emotions. Do it. And it's silly, but it will add up. Don't only check off your mistakes, count your successes. So, okay, moving on. Sorry for the spiel and the speech, but it's just, you gotta celebrate your wins. Don't just look at your losses. No, thank you, because actually your positivity helps so much. All of your positivity. I'm playing message tag with somebody in private, and I apologize for that. But, and what I see from my end that you guys don't see is lots of you private message by like saying the same things as one another. And the beauty of it is when you know other people going through it, it's like gives you permission, like, yeah, and I do feel this way and it's okay. And it is, just get better. Another form of cell notation, alphabetical. Anode before cathode. And do you do reactants or products first? Reactant to product. Reactant to product. Okay, there's a nurse equation. I'm going to completely ignore it because I don't like to do math. I like to dodge math. And I'm going to ask you this. If I want to get more energy out of a reaction, would you say I should add reactants or add products to it? So if I want to get more energy out of a reaction, dump in products or dump in reactants? So a couple votes in, dump in reactants. So is it reasonable to say more reactants equals more energy? So just based on that, tell me about choice A. Is choice A a situation where I have a higher amount of reactants or products as far as the ions? I don't care about solids in the equilibrium expression. So is choice A more products or more reactants? So I'll wait till a couple more votes are in. So the votes are even. Okay, finally, somebody privated. So in this case, again, this is reactant, this is a product, 0.01 or products, 1.0 reactants. So we agree 1.0 molar is greater than 0.1. Q does not include solids, absolutely positively true. So I can only consider this molarity of Zn2+, which is the product of the anode. So my product is 0.01, my reactant is 10. So I'm going to agree 1 is bigger than 0.01, 1 is bigger than 0.01. So I'm going to get rid of choices C and D because these have too many products, not enough reactant. Okay. And I'm now going to toss a little math in there and tell you E equals E naught minus 0.059 over N log of products over reactants. So does this math tell me the same thing? If I have more reactants than products, like we said, more reactants than products, that's a number less than 1. Log number less than 1 is negative. Negative added here would make it overall positive. Negative, negative, positive. So this corresponds with what we just said, which is easier, the math or the intuition that says reactants good, products bad. So which one do you think is quicker, easier, and just more sensible to you? Intuition, definitely. More reactants, reaction go more in the forward direction. More products, it hinders it, can't go as much in the forward. So now, how do I decide between A and B? Because they're the same number here, but what's different? Look at the E cell, okay? The one thing I want to point out, and I don't mean to nitpick on Coy's lecture, but he forgot to point out. So somebody asked about 2 electrons here. How many electrons here? He said it's 2. You always take that. This one, because one of them is 1 and one of them is 2, it's completely up to how the person writes it. But if you do it 2 electrons, then you need 1 of these and 2 of these. This must be squared. If you do one electron, one of these, half of these, this would be the square root of the molarity. He omitted the square that you have to have in there. That is why I don't want to do math, because it's easy to forget the square. So technically I should be squaring that, but what's 1 squared? 1. So I don't care in this specific lucked out, didn't screw it up case, but here I would care about it because you're squaring, because it's 2 electrons, 1 electron. So you need 2 silvers for every 1 nickel. So you'd have to square it for the Q. So just do keep in mind there's a square involved in that. But we've lucked out, we don't need to worry about that. From the table. Yeah, so the question is voltage concentration dependent? The answer is yes and no. The overall voltage, yes, depends on your concentration too, because this number is going to impact it. It's small, it's a tiny impact, but this number affects it. But is this number dependent on it? Or is this one defined with everything being 1 molar? Gotta mention something too. What are standard conditions? There was one that was put up there that the alarms went off, and I gotta mention this, and I don't know how to mention this to everybody. But what are standard conditions? The thing that leads to that knot. 1 atmosphere, perfect. It's actually, even though 273 is standard temperature and pressure for a gas, it's actually 298 Kelvin, which means in chemistry, we can't even get it straight what standard is. We change our standard, but it's those, and 1.0 molar. So 1 atmosphere, 1 molar, but not for H plus. So when he said pH of 0, and I was bummed nobody brought it up, that's not right. pH 7 if it's an acidic solution, or if it's an aqueous solution, excuse me. Because if it's pH 1, sure, or pH is 0, excuse me, 1 molar H plus, but that, what about the OH minus? You cannot have 1 molar H plus and 1 molar H minus. So this never applies to H plus and OH minus. P7 is standard, not pH 0. And you know what? I might be wrong. I don't know if Coy said it or if Josh said it, but somebody tried to convince you that it was pH 0. Take it back. I think it was Josh that said that. It's pH 7 is standard, not pH 0. Okay, was Josh? Okay, yeah. And when is it temperature 273 as opposed to 298? The only time, and this is such a pisser, but STP, it's 22.4 liters per mole for an ideal gas at 273 Kelvin and 1 atmosphere. That's the only time when we call STP, standard temperature and pressure combined, but standard conditions are these. So, oh yeah, I mean, we know what you meant, and you know what you meant, but yeah, and all I can do is just apologize why chemists can't get on board with the same thing, but they base this one on the freezing point of water, they base this on the pH 7 point of water. So it's just what it is. Okay. And is this okay? Did anybody even notice in his lecture he talked about standard conditions being pH of 0? Okay, so 1 noticed, 2 noticed. Yeah, it's not true. It's just not true. It's pH 7. And the one thing that is true is our body 298 is our pH 7.4. Okay, oh, Tiffany, I want to read what you added. Okay, yeah, so you just think of gas being cold. Makes sense, seems reasonable. And then, yeah, standard. Would you rather be in a cold lab or a standard lab? So standard conditions, not cold gas. I'll go with that. Okay, for this one then, back to table readings. So let me do it in red. I haven't done red yet. Zinc and copper. First thing, this one. gives me 1.10 because this is positive 0.76 now, that one. And then let's see, what other color have I not used? I haven't used black. So nickel and silver, this one's here. Nickel gets reversed. So that's 1.03. Which one's going to give me more voltage? 1.1. Perfect. Okay, so is this a question based on reading the table or determining reactants and products in either the Nernst equation or intuitively? So which one is it rewarding you for, or both? All the above. A lot of times questions will do that. One random fact, one random piece of information can take you from 4 choices to 2. But how many would agree the MCAT, you can never easily pick one? Okay, never strong. You rarely can pick one answer just straight out. It's usually you start eliminating things. So a couple answers get eliminated for one reason, then you eliminate another one for another reason, and eventually you're left with one choice. How many agree that's definitely what happens? Yep, standard condition. How do I know what standard condition? So Brooke, what are you recognizing that you want to tell me about that I will recognize this in the future? That standard conditions? Standard notation, that little circle right there is a thermodynamic term meaning those constraints. And so reality is delta G naught is under one set of conditions, delta G is under whatever conditions you have to be in. So if I heat something up, cool something down, it can shift a little bit. And so the difference between E and E naught, or delta G and delta G naught, predicts which way it would go if you just heated it, cooled it, pressurized it, did whatever you do to get it from standard conditions to actual conditions. Okay.
Is it okay
Onward.
if I ask really
Oh, yeah,
fast?
yeah, please. Yeah,
I meant like the notation of the answer choices. Is that a standard notation? That
oh, like you mean for this one?
products, reactant, anode, cathode, like just how the answers are written.
This is one of possible ways. And so what I try to do, this is a standard shorthand where you have the solid of the anode, the reactant, turning into the cation of the anode. Double bar means that separation anode cathode. So these are your anode reactions, these are your cathode reactions, always written from reactant to product in the anode, reactant to product in the cathode. That's one way to draw it. This one is another way to draw it, where they just named what the anode and cathode are, where they show the reactions. So there's like so many different ways they can draw this thing out. And so which way will show up on your test? Your guess is as good as mine. Maybe your guess might be better. Okay, somebody had asked about, a couple of you actually asked about going over questions from the handout today. And so really important thing to do. I want you to tell me, when I see a chair conformation, how do I recognize quickly and easily, because I'm lazy, what sugar it is? Is there a quick and easy way to tell? And I apologize, I didn't stick around long because I know about you, but I felt so bad. Simran seems so nervous. So I figured getting me out of there might help. So that said, though, did she mention the shortcut for chairs? So hand gestures for the Hayworth and Hayworth structure and the Fisher projection, but for chair conformations, quick and easy way to do this is to tell me the answer to this question. What do plants build their structure out of? What is so stable you can build a structure out of it? It doesn't decompose, it doesn't get broken down, and it makes perfect cellulose. In cellulose, then, you would want the structure to be highly stable or unstable. Highly stable. Equatorial is better than axial. That's one of the things we learn. So as a consequence, cellulose is made from beta-1,4 linkages of D, beta D, glucopyranose. I'm going to just stop there because I ran out of room. So when I see everything equatorial, then what sugar is it? If every last thing is equatorial, then what sugar? Beta-glucopyranose. Exactly. Okay, so what if something is axial? So for this sugar right here, would you agree there are two axial substituents? First, let's consider this one. This is the anomeric carbon. Why do I know it's anomeric carbon? Two bonds to O. Perfect. It's got two O's. One nitpicky thing, but can you have an anomeric carbon in a straight chain Fisher projection? Uh-oh, my connection just lost, so everything I've written here is going to be gone, not that I've written a lot. Technically, you cannot. Anomers exist in ring structures. So I'm sorry, just my connection died out. But you only get anomers. Oh, the question is, let's have some sugar like this. I'm just going to cut it off there. Is that anomeric? The answer is not yet. Is it going to be anomeric? Is that the one that's going to have two bonds? Oh, yes. Right now, it is not anomeric. It is on its way to becoming anomeric, but not yet. So now, is this one anomeric? Yes, because it has two bonds O in a ring structure. So when we talk about anomers, anomers are the alpha and beta anomers. The anomeric carbon defined based on the last carbon and the hydroxyl in the link. So here's my O here, here's my CH3 here. They're on opposite sides. So if I draw a line like this, they're on opposite sides. So that's alpha. That'd be an alpha linkage. I'm going to leave that alone. I don't care about the linkage right now. I care about what sugar is this. So if this is carbon 1, that's 2, 3, 4, 5, and 6. Are any of the hydroxyls axial? Which one is axial? Perfect. C4 is axial, which means, is this glucose? I think I need to change from JK to JL, not just kidding, but just lying. Trying to mess with us, go pre-med and mess everybody up. There's no room for that sort of thing. She's so testing. You know she's trying to troll you. She's not testing. That's totally troll. Oh, well, you can't read them. I can't write them. So I don't think we should ever send math messages to each other. This will fail miserably. But yeah, carbon number 4. So do you agree? Oh, you're too kind, but no, I don't believe my 4 looked too good as I just covered it up. Oh, okay. You have no more permission to speak ill of yourself anymore. I mean, whatever. It's C4. So with that in mind, I'm going to tell you, no, this is not glucose, because for glucose, everything has to be equatorial. If it's axial, that means it's a C4 anomer or C4 epimer. C4 epimer. What is a C4 epimer? A UCLA professor, probably one of the greatest OChem professors ever. I mean, this woman was just phenomenal. Taught in the 90s, she long since retired, but she had a way of teaching her class where she said, in her perfect world, her ideal world, she felt that there should be 2 men for every gal. That was a mnemonic. Politically, probably not cool nowadays, but guess what? Really memorable. 2 man for every gal, meaning 2 mannose exactly for galactose. So is this sugar a spinoff of galactose or a spinoff of mannose? Galactose, perfect. Because it's C4, those 2 are gone. And then what does reduced mean? Reduced means we added an O or taken an O away. Take O away. So deoxy has its 2 O's on 1, O on 2, O on 3, O on 4, O on 5 in the ring, but you agree it's missing its O on 6. So where is it deoxy? Meaning the best answer, this one. One last, I think, really cool piece of information. So let me ask you this. Do we digest di sugars or L sugars? So do we digest di sugars? Which sugars do we digest? We digest sugars that are D, perfect. So let's say you had a red blood cell and you want to put a marker on it to identify it for immuno reasons, let's say hypothetically. Would you want a sugar that can be easily digested and broken down, or do you want a sugar that we naturally do not break down? Which would be a better thing to have as an antigenic marker on your surface? Doesn't break down. So would you rather have an L or D sugar as part of what you have on your red blood cell? L sugar. This is actually L-fucose. If I number it, I'm going to do my best to number this, but priority number 1 is the O. Priority number 2 is the rest of the ring that has all this attached. Priority number 3 is here, and the 4 is the H. So if you were to put your thumb up and start with your fingers towards 1, so I want you to take your flat palm of either right hand or left hand. I don't care which one you start with. Put your thumb towards your ceiling, point your fingers to the right, and curl your fingers. Which hand, left or right, curls 1, 2, 3? So got left, 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 3 lefts, 4 lefts. So that means this is a left-handed sugar. Left means it is S. Either a doctor or you lose. That is an L sugar. That is a natural occurring L sugar. Kind of weird. Why would you want an L sugar on your antigenic marker? So your 3 sugars, the glycosidic protein or the glycoprotein on the surface, the antigenic marker. So we don't break it down. It has a 1-2 linkage, which is bizarre, and it has L, meaning this thing's not getting broken down. This marker is going to stay there to identify that particular blood type. So this is what you'd find on the surface of an O, somebody with blood type O. I can't type any day, so welcome to my world. Enjoy your 1-day visit. So anyway, so hopefully this seems okay. So that's where this question came from. And I don't know, it wasn't discussed in class. It didn't. The amount of time you got out early, I'm assuming the blood types weren't brought up. Is that true? Yeah. Yes, so excellent question. Everybody read Brooke's question, and I'm gonna go into it from an OChem standpoint. And in exchange, Brooke, you're gonna have to teach me some genetics and biochem. So fair deal, I'll show you the OChem, you teach me what I need to know next. Okay, so first off, blood type O is just like this, these 3 markers, but what's different, blood type A and blood type B have another sugar. They have another galactose as sugar number 4. Okay, does our immune system recognize something foreign, or does it recognize something that's missing? So if I put something into my system, I recognize a foreign material. So blood type O has these 3. Blood type A has galactose, blood type B has galactose with this weird nitrogen group instead of an OH. So if I'm blood type O and I donate my blood with these 3 on the same protein on the red blood cell, when I donate it to somebody A or B, am I donating something foreign or am I missing something? So when O is donated to A or B, missing something. So can O be the universal donor? Can O give to A and B and you don't recognize anything foreign? What happens in the opposite direction? If you take A blood or B blood has this forced sugar and you put it into blood type O, then what happens? I recognize the foreign body and I try to get rid of it. Meaning you try to put A or B into O, there's a foreigner. Put O into A or B, you're good to go. So what exactly is our universal donor? Blood type A, B, or O? O, perfect. There's also a rhesus factor. It's a totally different marker, but still in the red blood cell. You either have it or you don't. If you have the rhesus marker, you're positive. If you don't, you call it negative. So which is a universal donor, O negative or O positive? Which one is guaranteed to have nothing foreign? O negative, exactly, because they are missing the forced sugar, so you can donate. They don't have anything foreign, and without the rhesus marker, they don't have that other marker. Universal donor O negative, universal recipient AB positive. So does that make sense from purely the structure, the OChem structure we're dealing with here? Perfect. Now you get to teach me something. What happens to the second baby after an O negative mother gets their placental blood exposed? So let's say an O negative mother has a non-O negative child. At birth, the placental blood gets released and mixed. Okay, so during birth, placental sac's going to break, placental blood's going to get exposed to the mother. So the mother is O negative blood type, and the child is anything but O negative, anything positive or O or whatever. So the baby's cool because the baby's already been born and gone. We're perfectly fine. But the mom doesn't get attacked. The mom attacks the placental blood, other way around. So now the mother develops antibodies towards that foreign blood that now went into her system. So the mom's immune system turns on this foreign placental blood that now builds up antibodies. So in theory, can that mother have a second child that is anything except for O negative? Okay, so upon a time, how many ever heard, like old movie, maybe your parents talk about it, but did they have to get a blood test before they got married? Yep, once upon a time, absolutely mandatory for exactly that reason. So you didn't end up having immune responses to your kids. And I have no idea how it worked. If it was illegal to marry somebody of the wrong blood type, I honestly don't know. I don't know the legal history of it. But I think the state had to give you fair warning. Oh, by the way, you're going to have web-feet kids with 6 digits who will have immune weirdness. If it was the wrong blood type, it would start turning against it. Exactly. So kind of a cool little thing. Yeah. So, I'm gonna pile on your question, but somebody asked. So before I start dating, I'm not gonna identify gender, so it goes away. But before I start dating, on the first date, should I find out about their blood type so I know I should be serious on my second date? I paraphrased a bit, but oh, yep. So welcome to the new world of dating. In fact, your 23andMe, or if you have to be inbred, your 22andMe report should be standard material on your first date. Yep. Yeah, instead of what's your sun sign, hey, what's your blood type? Yeah, that'll go over real well. Welcome to geeky science world. Oh, I'm O negative. I'm one who's screwed. I can only take transfusions from fellow O negatives, and I don't believe I will ever give birth. Just a hunch. I don't know my bio well, but I'm pretty confident that won't happen. But yeah, interesting. Okay, so for what it's worth, does this make sense then? Going back to this protein's on the surface of a red blood cell. You have your protein, you have your 3 foundation sugars, and your 4th sugar ultimately determines it. Yeah, see, this is what you guys need to teach me the fetal. Yeah, but for some reason, I thought that the mother didn't develop antibodies until the massive exposure. Like when once birth occurs, then there's foreign blood and lots of it. But for some reason, I know you can exchange the placental sac, but does the blood exchange it? It would have to, because there's oxygen being transferred. But this is, again, you need to know your physiology much better than I do. And this is where I come up really short and cannot help you. And I would highly recommend Spencer. But for whatever reason, it isn't till the birth. So I think an O negative mom is good to go with one child, but after that, that's when the issues can start kicking in. That's where they actually develop antibodies towards that second one. Yeah, that sounds right. And the only reason I know this, my mom was O negative, I was O negative, my brother was not O negative. And so I was that high risk child, and my mom had to get some sort of immunotherapy to make sure. So my knowledge is strictly from when I was in the womb. And I got to be honest, I don't remember much from being in the womb, other than I felt very crowded and just felt like I had to get out. So. And please realize I'm just totally joking. I don't remember my time in the womb. Okay, onward I march. This one, just wanted to correct something. About 3 people messaged me about this, and I really want to make sure. 6-phosphofructose is ultimately what we're going to get. This is not one step. This is 2 steps in glycolysis. So I really want to emphasize this. Okay, amongst the errors, 1, you wouldn't have that 5th bond. I think everybody recognized that. But the other thing that's key, you have, the way it's drawn here, this is an aldehyde. This has to be a CH2OH. Then it's 1 step. Then it says phosphorylation step, where you phosphorylate and form 1,6-bis-phosphofructose. But you cannot have the aldehyde and the ketone on the same thing. You can't have 5 bonds, and this is there. So just don't worry. I was hoping, really hoping, you get just a couple of the revisits today of the glycolysis structures. But note that you go from, before this, you go from aldehyde form, the aldose, the glucose, to the ketose form, the fructose. What enzyme is responsible for going from aldose to ketose, going from glucose to fructose? Is it a kinase, an isomerase, a transferase, a phosphorylase? No, I'm just making crap up. If you're going from an aldehyde to a ketone, isomerase. Just want to just bring that up. Okay, and I don't know if I'm looking at, I'm not sure if person, well, the people, I think 1 of you, 2 of you might be here. Okay, terpenes. So, shoot, let me go back because I didn't want it to pop up quite yet. Okay, a couple things that I want to ask you real quickly. Have you ever heard of this molecule called acetyl-CoA? Does that sound vaguely familiar? Acetyl-CoA? Here's your acetyl group, sulfur connected to a CoA. What is acetyl-CoA responsible for doing in bio? Like what makes you know it? Why does it pop up? It's an energy storing molecule, perfect. So do we use it to build long chain stored energy? So what molecule specifically are you forming from acetyl-CoA? Fatty acids, perfect. How many learned fatty acids are always odd numbers? 1, 17, 411, 3,614, and 3? You mean tell me it has to be even numbers? Why would it have to be an even number? Oh yeah, gotta remember, TGL. Two carbons each time, exactly. So 2 carbons plus another 2 would be 4, another carbon 6, another pair of carbons 8, another pair of carbons 10, and so forth. So fatty acids go in long chains until you get to the very end where you have the CoA which eventually gets hydrolyzed, and you end up with your fatty acid. So how many have seen that before? Your fatty acid chain in the end. You build it, build it, build it, cleave it, there's your fatty acid. Okay, so if I told you a fatty acid had 23 carbons, you'd say, right on, you believe me, or I'm lying again. I'm lying again. Maybe it got modified, maybe some weird thing can happen, but 99% chance I'm lying to you. Okay, so perfect. You had all sorts of information about fatty acid chains. So now, what if I told you I did 5 plus 5? What does 5 plus 5 equal? 10. And what if I added another 5? 15. So can we actually build fats from 2 at a time, acetyl-CoA, but can I also build them from 5 carbons, things called isoprene units? Terpenes are built from 5 carbons, meaning 5, 10, 15, 20, 25, 30. Perfect. But more importantly, I also have to know how they link up. So here's isoprene. And you tell me what you think is going to happen in terms of connectivity. I'm going to call this 4 carbons and methyl. Where's the easiest spot to react in this molecule? The middle or the terminal ends? Terminal ends. Perfect. 1 and 4. So guess what happens when these things connect? You start getting this. You get 1 to 4 connections, you get rid of some double bonds. Ta-da, maybe you add an OH instead of this. But when you keep adding 1 to 4 to 1 to 4 to 1 to 4 to 1 to 4, you get this. Good question on the Diels-Alder. So let me introduce the Diels-Alder and hopefully mess with you thoroughly. Because again, as you know, how do I get job satisfaction? Messing with you and lying to you. Really, really hard to decide which I enjoy more because they're both really gratifying. But right now I'm going to go with messing with you. Okay. Again, 1, 2, 3, and 4. So in a Diels-Alder, absolutely right. A Diels-Alder reaction, you're going to see this happen. This is going to go down there. So is that making a 1 to 4 connection? Is that what I always expect, a 1 to 4? But now do I get this other funky, weird one that goes here? Now do I get a 4-3 connection? So weird as it may be, whenever I have a plus, I'm going to just mark that a plus is a 1 to 4 connection, plus is a 1 to 4 connection. But every now and then can it fold back on itself, much like a Diels-Alder reaction, where 1 and 4 connect, but then 4 and 3 back connect. So I'm going to tell you right now, beyond any shadow of a doubt, my 6-membered ring here means one of these is a 1-4 connection and one is a 3-4 connection. I don't know exactly which one, but I know that had to happen. So if I show you a terpene that's linear, it was a bunch of 1-4, 1-4, 1-4 connections. But if there's any 6-membered rings, it's like you said, a Diels-Alder, where you had a 1 to 4 and a 4 to 3. The only thing, can a Diels-Alder happen without heat or light? So for anybody who remembers studying this, did this take an intense amount of heat or intense amount of light? Perfect. Took lots and lots of energy to get it to go, which means it's not very probable to do this in just plain biological conditions. Instead, what you will find is there are some light reactions, like vitamin D have to have light exposure because one of the steps involves a Diels-Alder-like reaction, electrocyclic. But generally, we functionalize the molecule. So I'm going to ignore that for now, and I want to go to this question. So how many carbons total are there in this structure? Oh, no problem. So did she bring this question up or you guys ask this question? Okay, and did it go well? Sorry to have that kind of thing. Okay. Oh, well. So let me at least ask this. How many would agree this is 6-member ring, 7, 8, 9, 10? So how many are okay this is 10 carbons? Okay. So here's my second question. How many 5s do you have to add together to make 10? Okay, so there's definitely a 1 to 4 connection. I have one 6-membered ring, so that's going to be 2 connections. So 1, 2, but is there also this weird bridge right here? So how many new bonds did you have to put together to make this thing happen? You have to get the 5 plus 5 to make 10 carbons, but you have to have one ring here, 6-member ring, and the bridging ring. So right away, I need 3 bonds, not 2. How many are okay with that so far? That's a lot to make you can do. Yep, that rooftop thing. God, I love you for saying that. Thank you so much. But yeah, that stupid triangular ring rooftop thingy, it's a bridge. It's another ring. Yep. Oh, bless you. Because how many agree that that is not a ring? That's a bridge, the rooftop thingy. But you're absolutely right. There's 3 bonds total. I have this. Oh, you don't see the ring? Actually, best way to see the ring, get rid of it. So if I got rid of this line, so can you see the line I'm getting rid of that I'm whiting out? So when I got rid of it, that ring is gone. And then if I got rid of bond 1, now is there absolutely no ring at all? Nothing's connected in a ring. So to form a ring, if I want to form a 6-member ring, I need that bond. And if I want to form the bridge, I need that bond. So does that seem okay or seem reasonable to you? So that's what I mean by this bond here and then that bond here. Yeah, it's like 2 rings. You made 1 ring and then said, hey, that was so much fun. Let's make another ring. Let's make this thing so tied together like some weird sort of origami folded device that we're connecting everything we can. Okay, here's what I want you to do. Do I want you to identify the bonds here? Do I want you to work from the answer choices backwards? Which is the better way to go about this at this point in your estimation? How many are really good at recognizing 1 and 4 and 2s and you're set? How many can identify that's a carbon 2 because it has 2 carbons off of it? This is a carbon 2, so there's a 2-2 bond, so that one had to be formed. I mean, how many are really good at recognizing that that bond had to be one of the ones that formed? Honest answer. How many would agree that the only way you can have this highly substituted carbon connected to this highly substituted carbon is to make a bond between 2 and 2, which means that bond had to be formed? Does anybody see that? And not only see it, would that be your first thought for most of you? I need as many honest answers that way. Nope. 1 no. 1, are you kidding me? I'm going to assume kidding me means no. Another nope. Okay, so realistically, let's be honest. The odds of you thinking like a grad student in chemistry, yeah, if the leading question you would, but off the top of your head, that's not how most people are going to look at it. So trying to do it the OChem approach and label all your carbons, figure out the new bonds, that would kill you. Let's go backwards. I'm going to choose C or D. I don't care. I'm going to choose C because it's first. And what I'm going to do is I'm going to disconnect the bonds. So 1, 2, and 3. Let's disconnect them. So if I disconnect there, I now have that. If I disconnect at 2, I now have this. So let me just draw it. That carbon is all by itself. If I disconnect 3, I have this. Okay, so now I'm just trying to figure out what I've connected. So I have 1 carbon by itself here, and I have 1, 2, 3, 4, 5, 6, 7, 8, 9. So how many would agree I've had 1 carbon here and 9 carbons here? Ah, perfect. So Brooke, tell me what you don't think is good about this one that you just pointed out. You basically stole my question, dang you. No, don't be sorry. Actually, it's awesome you did that. So absolutely phenomenal that you did that. You need a 5 plus 5, not a 1 plus 9, which means it can't be C. I don't care how I connect it. I just know D is the last one standing. So how many can do it that way and recognize that you needed 3 new bonds because you have 10 carbons, so 1 5 plus 5 and 2 rings, a 6-ring ring plus this weird bridge. So 3 new bonds, and that you couldn't make 1 and 2 both because that would have had a single isolated unloved carbon in the reactant. It's not a 1 plus 9, it's a 5 plus 5. Honest answer, how many? All you can really do now is just let out a profanity. Damn. I mean, it's just, this one is just, it's a rough question. But the reason I threw this in there is because once upon a time, maybe on the MCAT, they had, oh, my thing did it again to me. Yeah, everything, screenshot now, because as soon as I light my computer back up, everything I've written there is gone. So if you want to screenshot it, now's the moment. Can you still see everything, by the way, on your screen? Okay, so I'm gonna try to get my thing connect. 3, 2, 1, connecting. No, so for, if it's not 5 plus 5, it's a totally different reaction. So the question was asked, said, is there a time that it wouldn't be 5 plus 5? Yeah, when it's 2 plus 2 plus 2 plus 2 for acetyl-CoA building it. But if we're dealing with terpenes, it's 5 plus 5. Now you might get 5 plus 5 plus 5 minus 1, where you have some post-translational, like post-synthetic change. But as far as the terpene chemistry goes, always 5 plus 5 plus 5. So it's got to be 5, 10, 15, 20, 25, 30, and you modify accordingly. And look, you got a fan who said okay to you. So perfect. Okay, so with this in mind, this question again, 3 new bonds, bicyclic, 2 new rings, and the 5 plus 5. And then you cannot isolate that carbon. So if bonds 1 and 2 are broken, that carbon right there is going to be left on an island. Only choice D is left standing. These are the pictures if you really want them. How many get very little out of pictures like that? How many get more intimidation than you do actually help? So this is for the 1 or 2 out of the entire class who were totally into OChem and had the professor went over the top on terpenes. It's recognizing skeletons. For whatever reason, and let me again ask this for anybody who's studied this before, on a lot of their practice tests and on maybe 1 out of every 3 or 4 actual MCATs, did you notice terpenes? So did anybody have terpenes on both lots of practice and on your real MCAT, at least 1? One yes, 2 yeses, 1 I don't remember anything from it. Fair enough. I had terpenes when I took it, and the main reason they put them on there, it's messing with you. Everybody studies fatty acid chains, so this is a way to give you something that's lipid related, but a little less familiar. So know the skeleton connection and you'll be in good shape, which leads us to 2 things. I want to revisit this real quickly because I want to do something MCAT specific. Isoprene, you cannot use this in your body because you cannot get 175 to 225 degrees Celsius, and you cannot get ultraviolet exposure except in your skin. So there are very few electrocyclic reactions we do. So instead, these are the 2 molecules that are actually active in the body. What does pyro mean? I can't remember that. I only remember what the word pyro. I mean, I'm a maniac for words, but I can't remember pyro. Fire. Pyrotectic, pyromaniac, pyro, whatever. So pyro. Pyro means fire, fire means heat, heat means energy. Yeah, no, actually physics. I'm done with the GChem part, sorry. So yeah, so the last part is physics. So yeah, the two other GChems are gonna bounce those until next sitting. Okay, pyro means heat. How many learned ATP gives you energy when you go to ADP? Is that something you definitely learned? Hydrolysis of ATP gives you energy. So is this kind of like ADP, where I can cleave it and go to AMP and give energy? So this is flat out awesome for two reasons. Number one, is this a bulky leaving group? So how many would agree it's a pretty good leaving group? So if I want to attack, I can definitely have that leaving group leave. Yeah, so sorry. Yours will be opening of next one, just because we got cut right on that cusp of how much got turned in. And I really wanted to go over specifically this. So, okay, so I have a leaving group, but number two, do I have a leaving group that can provide energy? So is this like having your own battery-powered reactant? It's got its own energy and a bulky leaving group. So pyrophosphates, whenever you see a pyrophosphate, you got to think like ADP, ATP, some stored energy going on. So if you have an unfavorable reaction, hydrolyzing it makes it favorable. Okay, perfect. Yeah, okay. How many actually did learn that? In pathways, you end up needing two molecules of ATP to get to AMP. For whatever reason, one becomes an intermediate in the transfer. I wish I could tell you why, but reality is you can cleave either one. And I think what happens, you cleave both, and another one comes in, picks up the phosphate, and then cleaves it. So I think you go from ATP to AMP, and then you go from an ADP to pick up one of the phosphates of the free pyrophosphate to release the other one and regenerate ATP. It's a weird pathway. And yeah, I don't remember having a professor that explained it. I just remember having a professor ask us about that. So ADP is an intermediate, but you end up needing two to regenerate. So anyway, just what it is. Okay, so for this one, the mechanism is this. Carbon number 1 is over here. Carbon number 2, 3, and 4, because that's my methyl. There's my 1, 2, 3, 4, and there's my methyl. So I've connected carbon 1 to carbon number 4, as expected. And I go to this. Okay, geranium oil. This is what makes geranium smell so wonderful. So why do I care about this molecule? The reason terpenes have a tendency to show up, they're used for markers, they're used for pheromones, they're used for messenger molecules. So how many remember hemoglobin having an alpha and a beta? How many learned there's 4 hemes on hemoglobin? 2 are called alpha, 2 are called beta. How many have learned that at some point? What's the difference between alpha and beta? They never make a big ordeal about it. One has a 10 carbon terpene, the other one has a 15 carbon terpene, meaning they're different markers. They can be identified differently when they're bound. So which is which? I believe alpha before beta, 10 before 15, but double check me on that. That's my memory from way back when I had it on a midterm 30 plus years ago. Maybe not 30 plus, but really close. But I believe the alpha 10, beta 15. But it's just a marker. And then why would geranium want to give off this wonderful smell? Oh, you're welcome. Wants to give off a smell because wants bugs to land on it, scrape their legs, pick up the pollen, fly somewhere else, and pollinate. And how many agree? If you can't move, you're a plant, you're stuck where you're at, you have to count on mobile things to come in, you attract them. Smell molecules. Okay, so 1 to 4 is a new connection. Typical thing that happens on the MCAT. How many have learned the here's a label, where's it in the end? How many have definitely in your MCAT travel studying and your real MCAT had find where the label ends up? How many would agree that has definitely been on your test at some traveling point? Guaranteed you're going to get it. So a couple ways I could do it. Number 1, I know that this is carbon number 1. That's one way, by knowing my connectivity, which means that's labeled and that's labeled. So in the end, that's labeled and that's labeled, that's labeled and that's labeled. Really great if I happen to know which one's 1 and 4. I didn't. So here's what I want you to do whenever you get these labeled ones. I can do it a couple different ways, but I want to do it a different way. This is my tertiary carbon. Here's my tertiary carbon. Here's my tertiary carbon. Is it easy to find the tertiaries? Look at the structure. How many agree tertiaries are super easy to find? So why look for a label that is really hard to figure out when something's already labeled for you? So if it's easier to find a carbonyl carbon, a tertiary carbon, some carbon like that, can I simply say, okay, here this, is it the one that's right next to it? So here's my easily recognized tertiary, it's the one next to it. Here's my easily recognized tertiary, there's one next to it. Tertiary, there's 2 next to it. So I got to decide, is it the one that has a lot of stuff or just one? A lot of stuff with an O, just one. There's my other one. Meaning if you're looking for a label, get an assistant label. So although I'm not labeled here, is it sort of labeled in a way that I can recognize it easily in the final product? You bet. When you do your AAMC materials, you're going to run into the find the label in the end on at least 10 different examples. It's a really common question. I challenge you, implore you, beg you to now label a different carbon, figure out where it went, and then work backwards and figure out if the label's still there. So does that seem okay? Is that how many would bind to that is, hey, that's not a bad idea. Recognize the other carbon that's easy to see and then connect to it. So take advantage of something that is easily recognized and work accordingly. Yeah, and you're not alone. There's a reason why I'm taking time to go over this right now, and that's because you and everyone else is one of those, what the hell, why am I doing this? It's really hard to chase it down. It's easier to recognize something that's structurally significant, structurally easily to distinguish. Okay, so moving onward. Tell me how to answer this one. Give me a strategy. Don't give me an answer, give me a strategy. Divisible by 5, perfect. So 5, 10, 15, 20, 25, 30. 10, 15, 15, 11. So absolutely perfect. So how many are okay with that? Count by 5s. Carbon for every finger. If you're inbred, you're a little in trouble here, but 5, 10, perfect. We're good to go. How many are also skeletal people? 1, 2, 3, 4, connected to 1, 2, 3, 4 with methyls coming off. Methyl, methyl. Those seem spaced far enough apart. Spaced far enough apart. Are these too close together? Are there too many of these carbons? So how many would also recognize weird skeletal arrangement? You have a choice to make. Recognize the skeleton, some are really good at that, or recognize 15 divisible by 10, or 5, 10 divisible by 5, 15 by 5, 11, not so good. So that's actually my answer because it's a not question, but hopefully it seems okay. So 2 isoprene units for A, check. And should I go slow because this structure is going to disappear? And so is anybody screenshotting this stuff, or do you just honestly not really care? Or is there potentially a way to take a screenshot at a future date if I screw you over? Okay, so screenshot. So moving on, that one's gone. Structure C, there's your screenshot if you want it. And I numbered it in a weird way. D is a nice clean picture, so you're screenshotting. And finally, B is in bad answer. 11 carbons, wrong connectivity. One more from the lecture. I want you to tell me which carbons were carbon number 2. Yep. Oh, look who's going to be a mean test writer. How many want to take the MCAT Brooke writes? That would be a pretty badass mean way to mess with you. Oh, sure you do. All you got to do is be mean. You don't have to know a lot. You just have to be mean, and you can become a test writer. And I'm just giving you a hard time being abusive, so please don't take my comments to heart. But this carbon is which carbon? I can't remember. Is that a 1 or a 2? Yeah, sadly, now test writers might know a little bit, but I honestly think that the truth of the matter is most of the test assemblers don't know what the heck they're doing. But here's a methyl, here's a 2, there's a 2, there's a methyl, there's a 2, there's a methyl. So I can identify this pretty easily. So that means I'm going to go backwards and say 1, 3, 4, 1, 3, 4, 1, 3, 4, 1, 3, 4. So is it the standard 1-4 connection? I mean, how many agree 1-4 is pretty typical? So there's my 1-4, 1-4, 1-4, 1-4. Okay. Second, was this a result, this final compound was a result of oxidation or reduction of something rich in alkenes, like an isoprene? So you see lots of hydrogens or lots of oxygens on this compound? Lots of hydrogens. So I'm going to get rid of oxidation as an option as well. Okay. Here's the question I have then. Would it be better, I'm going to start with isoprene. Would it be better to do a 1,4 addition to make the polymer and then reduce it to the polymer alkane? Or would it be better to go to isoprene, reduce it, turn it to an alkane, and then try to make the polymer alkane? Can you connect an alkane to another alkane? Are alkanes highly reactive or not reactive? No reaction. Meaning, in order for this to occur, you have to first link it up, make a polymer, then reduce it, or reduce it, then make the polymer. Sequentially, which do you have to do first? You have to link it up first. Isoprenes have to connect 1,4, then get reduced. Meaning this would be out of order. So 1,4 addition first, followed by reduction. So kind of a tricky little question, but you have to connect before you do the other one. It is a rough question. I mean, no doubt about it. And so, I mean, most people I think were able, 95 got one or the other. And I have to assume, my guess is I have to assume a lot of people just picked 1,4 because they just memorized that connection. I don't think it's really the logic. I think there was leaning towards D type of guessing. I think people actually knew what they're doing. Maybe a third of that group, maybe. Okay, terpenes, for whatever reason, popular in the MCAT. I still ponder it because I don't know why it's popular in anything, but it has some bio application and it's just an alternate way to ask you about fats. Okay, physics. So hopefully this is okay. Sorry for the quick turbo. Oh, you're so welcome. And it's, honestly, if it wasn't that tested, I would have blown it off and said, oh, whatever, answers this, answers that. But it really is one of those things that, and I wonder just real quickly, yeah, it is. It's for what godforsaken reason they like it, they just do. And again, I just can't tell you why it should be tested. I can't tell you why it's popular. It just is, and we kind of have to go through it. And I assume based on how early she ended, because I got an email from, I won't say who, but I got an email from somebody around 10:30 and like, you're in lecture, why are you emailing? And realized, nope, the lecture had ended. So I'm assuming she didn't go into the detail of this. And you kind of need it. That said, now that you see it, how many agree it's actually kind of easy? I mean, who would agree it's easy? I just never seen it before, so it's foreign. You can tell me the easiest thing in the world, but if you say it in a foreign language, I don't get it. And it's kind of what's going on here. There's nothing complicated, but if you've never seen it before, you're screwed. Now you've seen it. Now you get to play with homework, and it'll get better and better and better until you get to the point where you're bored and then you reach a conclusion, why am I doing it? You know, you're doing it because maybe they'll ask. Okay. What is the difference between kinetic friction and static friction? What is the fundamental difference of the two of them? Kinetic refers to sliding, two things sliding across one another. Static friction is where they are physically touching one another without any motion. So tell me, if two things are stuck together and not moving, can I safely say that's probably like a covalent bond or a really strong hydrogen bond? Two materials, and when you stick them together and they don't move, do you agree? Probably are bonded together pretty tightly. But if I have two materials that I can slide one across the other, then they're probably tightly bonded or not as tightly bonded at the molecular level, one surface to the other. So if one surface can slide across the other, probably has strong or weak intermolecular forces. Not as tightly bonded, weaker intermolecular forces, weaker interactions. So which is a stronger interaction, mu-S or mu-K? Mu-S. Chemistry says so. Static friction holds things together much more tightly. Okay, so here's what happens. Static friction is always there, or is it a reactionary force? And let me step back. What is a reactionary force? What do I mean by a reaction force? Perfect. Newton's third law, equal and opposite. Only happens if you do something to it. Push on a wall, it pushes back. If you don't push on the wall, nothing happens. Pull on a rope, it will pull back with tension. Don't pull on it, there is no tension. Static friction doesn't exist unless you push off. So I want to walk. I'm standing perfectly still and I want to walk. Do I have to push on the earth so the earth will push back on me and I can move forward? That can only occur as a reactionary force, which means I can only push on the floor and have the floor push me the other way if there is such a thing as static friction. So from now on, I'm no longer going to use the word static friction. I'm going to use words like grip, traction. I mean, do they have good traction on your tires, good grip on the bottom of your shoe? Those are just common ways of saying a large mu-S where your shoe grips the floor, your tire grips the road. So better mu-S, you can turn faster, you can accelerate with your tires faster, your feet faster, you can move. The problem is, if you push off too hard or you accelerate too much with your tires, do they grip or do they eventually break free and start spinning? Does your foot slide out from you? It begins to slide. Meaning, is there an upper limit based on your personal experience? You can only push off so hard before your foot breaks free, meaning can static friction only go up to a certain threshold and then you break the bonds and it's kinetic. And once it's kinetic, you're screwed. Meaning it's terminating, okay? So picture this for me. I want to start walking on my floor. If I go off really gently, can I do it? If I give it a little bit of gentleness, I go a little bit firmer, 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 and then I'm screwed, I'm done. How many agree? I can keep pushing a little harder, a little harder, a little harder. In fact, how many have done this? You have a box you're trying to slide across your floor. You push, you push, you push, 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 and then finally when it breaks free, you fall flat on your face and it shoots across the room. How many have experienced static turning kinetic in an embarrassing way? Yep, or you're trying to undo a screw, turning, 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 and then all of a sudden when it goes, your knuckles smash into something because your hand flies. Welcome to the static becomes kinetic world of knuckle scraping and falling flat on your face while sliding a box. Okay, all things that you have firsthand experienced that, oh damn, kinetic is less than static, said the chin to the knuckles as they were both bleeding. Okay, so now I'm gonna figure out what's happening on a rooftop. You're on a rooftop like this, very minimally sloped. You're gonna slide down or not slide down? You're probably fine. But if we start lifting that rooftop up to, let's say, right here, Now what happens? Now are you not so fine? You are done, because mg sine theta is a resultant vector taking you down that slope. The only thing preventing you from falling off is static friction. That's the only thing preventing you from sliding down that roof, which means if I start lifting that roof higher and higher and higher, eventually, am I going to reach a point where the mg sine theta, because it gets so steep, is too much and you no longer can grip as well? So tell me what your instincts are. If you were on a platform like this, you don't want to slide off and it keeps on going up and up and up. What does your instinct tell you to do? It's not so much US as much as it is static friction total. It's more the normal force is decreasing. Laying on a floor, the floor pushes up a lot. On a wall, it doesn't push as much. But what do you do, Michaela? If you were on this roof, what would your instincts be? To try to grip more tightly or less tightly? Pry your fingernails in? Right. So would you instinctively try to raise your mu-s to make up for this? I can't do anything about normal force. I can't suddenly gain weight. So I'm going to claw in and try to save my life by clawing in. I am instinctively making us go up until eventually even my fingers won't be able to hold me in place. So if you think about Spider-Man, and I'm sorry to be gender specific here, but I believe, is there a Spider-Woman cartoon? Sorry to be ignorant. But, and I always want to deal with the real world like this, like Marvel characters, but what's true of mu-s? Mu-s is higher or lower for superheroes? They increase their mu-s. There you go. See, that's important knowledge. Now you can truly be a doctor, now knowing that. Okay, so let's go back to this. Static friction is going to go up because it's offsetting it. It's going to go up, go up, go up until you're screwed and you slide down. It doesn't start higher and get lower because the angle is going up, not down. So in this case, the inclined angle increases. So that's what I'm looking at right here as it increases. So, and then it goes up until it terminates. So that's my best answer. Notice it's curving a little bit. Is that for a reason or is that to mess with you? And this was highly inspired by something I may have possibly seen in my lifetime of exposure. There to mess with you. In a perfect world, it's a straight line. In the real world, materials start to deform a little bit, and so it's never quite perfect. But it's not going to start high and decrease. It's not going to stay constant. It's going to go up as the angle goes up, but it doesn't go up and suddenly go down. It goes up and terminates. So does this seem okay? Does this answer choice seem reasonable to you? Okay, perfect. So moving on. The picture that is so far off that you cannot visually look at this. So I need information from the passage. So if all of you want to play along with me on page 72, this is called I didn't copy everything I should have, even though the person submitting it gave me everything I needed. So my apologies in advance for being so poor. And I'm going to ask you to give me some assistance on the reading of numbers because admittedly, I'm in a poorly illuminated room at the current moment. But what is the mass of the pan? Mass of the pan all depends on where I balance it. So here's what I have to know. First and foremost, is the bar centered or off-centered? So if I just had the bar like this, you expect it to stay there, or would this side start to fall? Off-centered. Okay, so that's one of the torques. A torque is anything that can get it to turn. So I'm going to say, I want to consider the bar first and foremost. And then there's the counterweight. I'm going to get rid of the counterweight as drawn here because it is just misleading as can be on this question. The counterweight, they say, is right here. Would you agree? I mean, according to the passage, does it say it's like one centimeter? Is that what it is? I'm going by memory. I mean, literally, I'm in too dark a room. My eyes just way too jacked up right now. So 1 centimeter. So that is the mass, and the mass is 0.5 kilograms. Does that sound about right or no? Okay, perfect. And then tell me about the pan. Ah, the rod is 0.5. How much is the mass? Mass is 0.01. And then the pan is some unknown mass. So you tell me intuitively, looking at this, how significant is a tiny mass 1 centimeter compared to a heavy bar way over here? Which you think is having the bigger impact? The bar is heavy, the bar is there. So I'm going to go on a limb and I'm going to tell you this is 20 because that's half of 40. And so how far is it from 10 to 20? So if I'm considering just the bar, I would agree that's 10 centimeters for just the bar and 10 centimeters for the mass. How many are okay with that? That this heavy bar and the pan over here. Okay, so if the bar is 0.5, you agree this has to be at least 0.5 kilograms, at least, not more. Okay, so the pan has to be this, just this offset the bar. And should it be a tiny bit more or a lot more? What does your intuition tell you? Plus a tiny, tiny bit to help balance out the weight. For a grand total of 0.5 plus a tiny bit, which leads me to think it's this one right here. That's intuitive. That's visualization. But should I also do it by math? So how many are okay with considering? First thing I had to decide, how many things are fulcrumed up? How many things are offset? 1, 2, but also the bar, 3. The bar is off-centered. So I considered the bar, the weight, and the pan. Okay, so now I considered the pan has to offset the mass and the bar both. You told me bar is heavy and far away, mass is light and close. So the far away heavy one is the first thing considered. And then the second one, just it's just there. Mathematically, I would have to do the following. Force times moment arm. I'm going to do moment arm in centimeters just to be this, but force times moment arm is torque. I don't know why I crossed it up. I always do that. My apologies. So on the left side, I have unknown mass times g times 10 centimeters. On the right side, I have the bar, which is 0.01, sorry, 0.01 g times 1 centimeter plus 0.5 kilograms, I'm sorry, times 10 centimeters. Can I ignore my g? Sure, that's out. So on one side I have 10m, and I'm going to completely ignore the units because everything's centimeters now, equals 0.01 plus 0.5 times 10 is 5. So overall, I now have, I apologize, I got to do this over here, but 10m equals 5.01. So m equals 5.01 over 10, which equals 0.5, which confirms choice B mathematically. Which way do you prefer, math or intuition? Intuition. Which way do you feel like you're cheating and it's not doing it the right way and you have no confidence, math or intuition? There's our dilemma right there. And how many agree that's exactly what I have always felt? Because every physics professor you ever had taught you math. You go to the MCAT class, they teach you math over and over and over. You and only you can start believing in the intuition. How many get it right intuitively, but you just don't feel confident because you didn't do math, and apparently you haven't done math until I boxed an answer. Now, I feel complete. I put a box around something, so I must have done something really good. I, again, beg, implore, whatever word I'm fishing for, you to start trusting your instincts more and more. Every time you get something right intuitively, celebrate. Pat yourself on the back, give yourself a little star, write a little I kicked butt or a smiley face or something, but reward yourself for doing intuition right, and eventually start to believe it and trust it more and more. And then on the MCAT, you're going to use it sometimes. You're not going to trust it all the time. It's not going to work all the time, but it's going to work faster and with less careless mistakes. And I mean, it's only going to come with time and practice. So yeah, I'm assuming you meant that the other way around. Yeah. Yeah, your intuition will tell it right, then you'll do math and it won't match it. And like, oh, I better go with math because, you know, physics people in the front of the classroom are smart. They do math. So therefore math is good. I don't deny math works. And I'll be the first one to admit, I've certainly solved more things math-wise than I care to admit. But intuition, you got to trust it. Oh my gosh, not drawn to scale. And the MCAT loves to throw that in there. And you can guarantee pretty much they're always drawn to scale. They just say that because of some anal student who will say it wasn't drawn perfectly. They plucked a hair out of their head and measured the exact number of hair length width. So, oh, you're welcome. Oh, you're very welcome. I hope you like both ways. Is it okay if I keep going a little bit more? Okay, if that's okay. Yeah, there's just a few more questions and I kind of want to get through it so I don't carry too much over. How do you run? How do you walk? How do you do any of these things? You go from stationary to moving. What do you absolutely have to have if you want to be able to get out of the blocks fast? You want to be a better runner? You want to start off and be able to move faster, more efficiently? You gotta have some traction on those shoes. You gotta have good grips. So the normal force allows runners to get out of the sprinter's starting blocks. True or false? Yep. So static friction. Yeah. So the static friction gets it out. But what is a block? So this is what's sort of interesting because it's twofold going on here. It's static and normal force. So if you were just running, it's purely static. But starter's blocks, you agree, are like this, and the shoe is sort of pressed against here, connected to the person about to run. So it's like pushing off a wall. You're pushing here, and it's pushing you back to get going. So how many find you can get going faster running out of blocks than you can just on flat surface? Okay, so the normal force, the slope surface here, that normal force is actually helping it to the foot to push off. So that's looking true. And to double check, it is in 1, 2, 3 of the answers. So I'm feeling pretty good. If I only found it in one answer, I'd be really nervous. Find it in 2, that'd be fine too. Static friction can speed you up and slow you down. True or false? Okay, this is the one that really bothers people. It can definitely slow you down, Oh, can't slow you down? So let's figure out how these things work. Can I start walking? Can I go from not moving to moving by having good traction on my shoes and having grip the floor and push off? Which means, can I speed up from 0 to whatever speed I've gone to, whether I'm running or walking? So will you agree static friction can speed you up if you have the right shoes on the right surface? Socks on wax floor, no bueno. But on the right surface, you can speed up as long as you don't slide out. Exactly. Now, can you slow down? Meaning, can your tires on your car cause you to stop without actually skidding? If you just take your foot off the accelerator, can the grip of your tires on the road actually slow you down? That interaction between the two surfaces? Can I quote you on that? Somebody put something awesome in the chat box that's just so perfect. Yes, as long as you change tires when needed. Ah, yes. How many like me, when you were a broke college student, or after college was actually just as bad, how many ran your tires to absolute nothingness? I am so embarrassed to admit this, but I actually, once upon a time, put super glue and duct tape on my tires, like this cheap ass patch, to make them last just a few more weeks till my paycheck came in. So it just is what it is. Yep, it's just what we do. Yep, and we've all been there, but yeah. And I actually used duct tape to patch my pants for lab. So it became a fashion faux pas that I was okay with. All right, this is true. 1 and 2 is true, so that's out. And then 3, normal force responsible for running on a horizontal surface, true or false? Now we need you, Jonathan. You own this one, or I forget somebody who said it earlier, but. So on a slope surface, normal force helps, but if it's a flat surface, F static equals F reactionary. Yeah, on the horizontal surface, it is purely F static. There's only a normal force when you're running out of blocks. So the starting block. So how many would agree this is just a nitpicky, tricky question? I sincerely apologize, because in GChem, on a couple chapters, I put something called LQ, and I really should do this more often. LQ is the everybody gets it wrong, but you learn something. So, okay. And it's kind of weird, because to me, I never understood why a rolling tire was static friction. That's what really bothered me. But if you think about, if you had, let's say, a whole bunch of shoes like this connected in a circle. So here are all my shoes connected in this weird circle. And if I could somehow walk across this, where I have one shoe grip and then the other shoe grip and the other shoe grip, kind of like a tractor wheel, they each are going to push off just the right amount. So I decided for it to get me going, but could it also be the other way? Could I go backwards? If I'm like moving forward, could I backpedal to try to push myself the other way to slow me down? So tires can move in either direction. The static friction go in either direction. So the fact your car can coast to rest is static friction. Yes, yes, that's exactly it. There's static friction at one point because it is or is not sliding. Is it gripping or sliding? For the briefest of seconds, gripping, which implies static or kinetic. Static. Absolutely, positively perfect. Exactly. And honest answer, how many find the word traction and grip much easier to grasp and comprehend than the word static friction or the concept of µs? It is so much easier to word it in ways that we speak. And again, that's one of the things. Do you only do that if you have enough confidence and trust yourself to translate? Yeah. And this only comes with buildup of time. And part of, at least, and I'm going to go off my own tangent, I think part of the struggles people have in physics is it's taught by a mathematician who shows math and maybe applies it in real life. Which if you learn it in reverse order, real life examples and how things work, think like an engineer, you will do so much better on physics and this test. But you need to give yourself permission to trust. Okay. Oops, sorry, I double pumped. For the following, which following statements, what is true? Okay, just real quickly. Oh yeah, everybody read and repeat Brooke's comment, because how many find that to be completely true? How many would definitely agree? Yeah, high school teaches it better than college. Okay, so I have a question for you. If I put one rope on a mast, one tension, I can lift it up. What if I put 2 ropes or 3 ropes? Would that be triple the tension? How many agree the more ropes I can have lifting something up, the better or worse in terms of lifting it up? What's your intuition tell you? 1 cable or 3? If you have 3 cables lifting up, it's going to go much better than 1. Makes sense. What about this 4th cable I attached there? You'd say good call, or is that something doesn't seem right? To lift it straight up, is it better to have the cables go straight up or at an angle? Which means I'd have to rewrite it like this. That part isn't going to help me at all, but this part is. So would you agree this is T times some angle? I'm going to put a sign in there because I know what it is, but how many agree that this one isn't giving you the full thing? This one's only giving you a certain portion. If you want to know how a pulley works, if you want to understand a pulley, count your vertical ropes. So here's the weight that's moving right here. How many things are actually lifting it? How many things are actually attached to this and lifting it? 2. And all of it, or is it a weird angle? So T1 sine theta, and on the other side, T2 sine theta. Perfect. So that's what you're dealing with. Over here, I'm only pulling 1 rope. So basically, have I turned 1 tension into 2 and made it easier to lift? But here's the catch. Can you create energy, or is energy conserved? Perfect. Energy is conserved. So therefore, I can make the force greater, but I cannot make the energy greater. So what exactly is energy in this case? Well, energy is work. Force times distance has to be a constant. Energy is conserved. So if I were to pull a long distance, I would do it with small force. Over here, I would get this to go up, lift with a large force. That's an F. So lift, let me try to make this more legible. Lift with a large force over a short distance. So energy conserved, meaning if I can pull this a long distance, but with a small force, can I lift this something really heavy, but a very short distance? Mechanical advantage is the force you get out divided by the force you put in. Tension in a rope, because these are perfect massless frictionless pulleys bought from Costco, because that's where they sell anything and everything in bulk. So these 2 tensions sine theta equal that. Tensions here have to equal this. So we end up with mechanical advantage being the following. Mechanical advantage, what you get out over what you put in, T1 sine theta plus T2 sine theta over T. Well, it ends up T1 and T2 are the same thing. So mechanical advantage is just going to simply equal 2T sine theta over T, which ta-da, 2 sine theta. How many are okay with that math, that I guess, harebrained sort of math of the system? I mean, that's mechanical advantage. You can follow it, makes sense. How many were much better off when I said how many vertical ropes? How many could go 3 and a little bit visually much easier than my math derivation? Math derivation is completely spot on correct, but is this much easier? So I ask you, what's mechanical advantage? Well, it's 2 sine theta because I derived it, or is it 2 vertical ropes that aren't quite vertical? So mechanical advantage is 2 times something to make it a little bit smaller because they're not perfectly vertical. How many can see 2 ropes that aren't vertical and say 2 times some non-verticalness, figure out what that is, as opposed to going through the math? Then that's what we're going to do. Mechanical advantage is this. Okay, things that are true. The system only provides mechanical advantage when the angle is between 30 and 90. How many would agree you get it higher and higher, do these angles get to become ineffective and don't help anymore? Ah, perfect. You can see and feel A. Mathematically, I'm sure there's some truth when I do sine of 90 is 1/2, 2 times 1/2 is 1, 1 over 1 means mechanical advantage of 1, it's no longer an advantage. How many agree 90 degrees, they're vertical, that's a lot of advantage, but as the angle gets worse and worse and worse, goes down. So how many could say small t? Intuitively, it makes sense. Vertical, great. As I get less and less vertical, it's less and less of an advantage. Okay. How many learned that tension in a perfect system, tension here equals tension here equals tension here? All it fully does is redirect the direction, but doesn't change the magnitude because they're always massless, frictionless. Looks pretty good. I'm going to go small t again. Mechanical advantage increases the more you raise the weight. So what's your intuition? As you keep on lifting it, does it get harder or easier to lift? Gets harder. Not easier. So that's false, true and true. That's your answer. Again, intuition or math? Math works, do not get me wrong. Math will work. Plugging in sine of 90 is 1, so mechanical advantage is 2. 2 sine of 90 is 2 over 1. So mechanical advantage of 2. If it's 30 degrees, it's 1. Mechanical advantage can only be an advantage if your numerator is bigger than your denominator. So this pulley system only works to about 30 degrees, then it becomes sort of silly. It doesn't work anymore. Mathematically, it just makes me feel more confident in my intuition. Math is an assist, not a source of solving things. And then how many just know this, that pulleys redirect tension? Hopefully that's one of those that's just sort of programmed into you. Yeah, somewhere along the line, somebody said it and probably believed it. Okay, one last question submitted. And again, I apologize for going so over. The most ideal boat design. This one is just a weird passage, and I don't know why I leave it in here because this is actually from so long ago that they had, but what they're talking about is they shoot water across the bottom of this boat. What do you want for a boat? You want a boat to have a lot of friction moving through the water, or you want it to move easily through the water? You want it to move easily. So instead of moving the boat through the water, can I blow the water across the boat and is it the same effect? Sure. So if I blow the water across the boat and it pushes it back a lot, what does that mean? So I connect it to a spring here. I blow the water across the boat. If it pushes a lot of friction, which is a good or bad boat? Bad boat. So you want it to barely move or move a lot? Barely move, so you want a large or small delta X? Perfect. What else then? You want it to be fully submerged, partially submerged, mostly floating? Mostly floating. Is it easier to move the water or air? You nailed it. Less friction. So is this one you could only do intuition? Yeah, I mean, you could come up with a math equation relating kinetic friction to the shoot speed and contact area and be great, but so much easier when you do this. So this one I'm going to assume is just pointless to even throw some math at it. So you can pretty much, I mean, it's a waste of time in a minute per question to do anything but that. So that covers it. Let me just double check. Yep, that's the end of the thing sign. I love triangle charts, keeping track of things. So hopefully this seems okay and that you'll do well on your MCAT. Sorry, I just couldn't help but do dumb things. You're welcome. I'm sorry office hours always turn into that, more of a lecture, but thank you guys. And I mean, again, thank you for taking care of each other. Really just greatly appreciate that. And at some point, Jonathan, I need some advice, probably in a medium that isn't transmitted down the road. You're very welcome. Thank you guys. And seriously, thank you for being so kind and good to each other. That's going to pay dividends. And I got the coolest email today from somebody who got accepted and was talking about the fact that when they interviewed at some place, they actually stayed with somebody they took the class with that they met in class. Those who was in person. And they said that made all the difference. They drove them to the school, told them all about the school, and they got in. That was like their acceptance. And I thought that was so awesome. And just somebody that just happened to sit next to him in class that happened to be from Michigan, but living out in California. So they stayed with their family when they're back there. And it's like, I love it. That story just made me so happy. It makes me so happy.